putting the arrows together to explain the formation of alkenes. Since the alkyl halide is crowded at the alpha carbon, the base cannot act as a nucleophile and go through the SN2 process. Instead, the base attacks a beta hydrogen, which allows the negative charge from the base to be transferred to the halide-leaving group. The result is a stable anion, the halide, and an alkene. If more than one type of beta hydrogen is present, regioselectivity is possible, with the Zaitsev isomer being favored. Cis and trans stereoisomers may also be possible. One of the more subtle ideas within how the E2 mechanism operates is how the relative orientation of the beta proton and leaving group affect reaction rates in a profound way. In this example, the two cyclohexyl bromides react with base at quite different rates to give the same alkene product. These differences need to be explained. Firstly, the large T-butyl group is used to lock the conformation of the cyclohexane chair, since the large group will always need to be in an equatorial position. This means in the cis isomer on the left, the bromine group will always be axial, while the same group on the right will always be equatorial. Next, we must consider how these orientations will impact the energy of the transition states that lead to product, since we know the E2 is driven by transition state energies. In the cis isomer on the left, the beta proton and bromine leaving group are anti to each other and coplanar. This means that the sigma bonding orbitals that need to become the pi bond in the alkene are already aligned parallel and require minimal reorganization to make the alkene. On the right, those sigma bonds are aligned in a gauche conformation, which means the molecule has to twist to become aligned for the pi bond. That means more energy, which means a higher transition state and a slower rate of reaction.